Hello everyone. Today we are going to start our new topic, that is the photochemical reactions. This topic is very important as it will be also covering the syllabus from NET and SET as well as competitive exams. So let's start with the topic. Am I audible? Answer me in chat box. Am I audible? Okay. So let's start with the topic. So myself, Mrs. Swati Villekar, and we are going to cover the topic from photochemistry unit, which is the photochemical reactions. And for this, we have already seen some basic concepts like in case of unimolecular reaction, there may be the internal conversion or intersystem crossing. These are the non-radiative pathways. As well as we have seen some radiative processes such as fluorescence emission as well as the phosphorescence emission. And there may be some processes where instead of all these internal conversion as well as the fluorescence or non-radiative pathways, it will show some quenching process. And in the last, which we have seen about the electronic energy transfer, these are the probable mechanisms. We have already seen it. So there may be the excimer formation, which is a when we are saying when A molecule is reacting with B and A is in the triplet state, at that time it is transferring its energy to the B molecule, and during that process there may be the four possibilities which can occur. Firstly, there may be the excimer formation occur, or there may be the exiplex formation will occur, or A-type delayed emission of fluorescence will be there, or P-type delayed emission of fluorescence will be there. So all these are the different processes which can occur. Now our topic is photochemical reactions, out of which we will be going to cover. Under that photochemical reaction, you have to study the reaction of ketones, olefins, conjugated olefins, and aromatic compounds. So we have already done it on Google Meet for practice session, and now we are going to finalize this. And the next topic will be photosynthesis, which we will cover in next lecture. So starting with the topic, the reaction which is initiated by heat is called the thermal reaction, and a branch where we study such reaction is called as thermochemistry. Now, as the reaction is initiated by heat, it is called as a thermal reaction, and the branch is called thermochemistry. So the reaction which is initiated by light is a photochemical reaction, and its branch is referred as photochemistry. Means when you are going to write about the photochemical reaction, you must have to write H nu there, which is a photon is being absorbed there. So in organic molecule, electron present in sigma bond, pi bond as well as the non-bonding molecular orbitals. As you have seen in syllabus, you have to study the reactions of ketone, olefins, aromatic compounds, etc. So when you see about the organic molecule, at that time the electron may be present in sigma bond as well as pi bond as well as the non-bonding orbitals. So therefore, when it is bombarded by the UV as well as visible region, then electrons are excited from bonding molecular orbital to anti-bonding molecular orbital. So for that I have given different transitions. So the molecule may be gets transferred from bonding molecular orbital to anti-bonding molecular orbital, and this is the diagram for that. After absorption of radiation, there will be sigma to sigma star transition, n to sigma star transition, pi to pi star transition, as well as n to pi star transition. Now, as the electronic excitation is quantized process, that is, the excitation of any transition is required specific amount of energy. As the electronic excitation is quantized process, it means every excitation is associated with some amount of energy changes. It may be 1 h nu, 2 h nu, 3 h nu, like that. So for excitation of any transition, it requires specific amount of energy, and therefore upon irradiation of suitable electromagnetic radiation, it causes specific transition, and this transition is well explained by the Jablonski diagram, and for that we will study the Jablonski diagram. So what is Jablonski diagram? That it is the diagram which explains the fate of excitation of electron from ground state to excited state when molecule undergoes excitation, which we have already seen in earlier lectures also. That is, when the electron is being promoted from the ground state to that of the higher excited state, it has the probabilities which may be internal system, intersystem crossing, internal conversion, non-radiative pathways, as well as the radiative pathways. Or there will be some quenching process also there, or there will be the exiplex formation, excimer formation, and p-type delayed emission of fluorescence or e-type delayed emission of fluorescence. So all those are the possibilities which may occur when the electron gets promoted from ground state to the excited state. So with appropriate frequency of electromagnetic radiation, specific transition can be worked out. When the electron undergoes into excitation from ground state to the excited state, the ground state singlet is converted into excited state singlet S1. Now, as you are knowing the diagram of Jablonski, you can easily just compare that. You should have the diagram in your mind for that. So during electronic excitation, according to selection rule, spin of the electron should not get invert. During electronic excitation, according to selection rule, spin of the electron should not get invert when it is being transferred from S1, when it is being getting transferred from S3 to S2 state or S2 to S1 state, that is in excited state, singlet molecule undergoes into vibrational de-excitation and it is called as the internal conversion. When the molecule is coming from S3 state to S2 state or S2 state to S1 state, so this is called as the internal conversion process. The excited state singlet is unstable, so it has a lifetime of 10 raised to power minus 11 seconds. Therefore, it is highly unstable. To achieve stability, it will undergo into internal conversion as well as it may rebound back to ground state. That is, it may come from S1 to S0 state and at that time it will emit some amount of energy and that is called as the fluorescence. So this is the Jablonski diagram where the molecule will be transferred from, this is the singlet state and singlet state is associated with the vibrational state and vibrational states are associated with the rotational energy levels. So just assume this is the singlet state in ground state and S1 state is the first excited singlet state and this is the triplet state. Now molecule has, when the molecule is being promoted from the S0 state to S1 state, then it has the possibility either to come from that S1 state to S0 state or it has the possibility to go from S1 to T1 state and this is called as the intersystem crossing. That is, the molecule may undergo into spin inversion process where the singlet is converted into triplet state and this conversion is referred as the intersystem crossing. And here just remember that when the molecule is being promoted to the higher excited states, at that time the spin of the electron is not undergoing any changes, but when it is going from this state to this state, at that time you can just observe the spin gets inverted in the triplet state. So this is the main thing for photochemical reactions. Spin inversion is the main process for photochemical reactions, because if the spins are anti-parallel to one another, then only the bond can form. So in triplet state, molecule experiences less electronic repulsion and therefore it is more stable and has lifetime of 10 to the power minus 4 seconds. In triplet state, molecule experience less electronic repulsion and therefore it is more stable and has a lifetime of 10 to the power minus 4 seconds. Where we say the molecule, when it is showing the fluorescence, at that time it is having a lifetime of 10 to the power minus 8 seconds. But as it is undergoing the spin inversion process, so it will require some time period for that, and so that's why its time period come becomes 10 to the minus 4 seconds. So in triplet state, molecule has sufficient time to react. So you can just assume the reaction which is occurring here, the molecule is being there for 10 to the minus 11 second, very short time. Then here the molecule is being there for 10 to the minus 8 second, again very short time. But here in triplet state, it is staying for 10 to the minus 4 seconds. So it has a sufficient time to undergo reaction. So when molecule undergoes into de-excitation, that is from D1 to S0 state by spin inversion, it emits energy, and that is called as the phosphorescence. This phosphorescence is a delayed phenomenon because of the spin inversion requires some time, and it has been observed that energy gap present in S0 to T1 remain fixed for any particular type of transition. Now, as we are saying, the molecule on the absorption of some amount of energy, molecule is initially in ground state, that is S0 state. On the absorption of some electromagnetic radiation from UV as well as the visible region, just remember the region, it is a UV as well as visible region. At that time it gets promoted to the higher singlet states level. Now when it is being getting promoted to the higher singlet states level, at that time it has the possibility to come back to ground state with the emission of fluorescence. Second, it may undergo fragmentation. Third, it may undergo internal conversion. Fourth, it may undergo intersystem crossing. Now if the molecule is crossing the is coming through the intersystem crossing, then it will come to the triplet state. And from in that triplet state, as the molecule is staying for just longer time period, that is 10 to the minus 4 second, it has different possibilities. Like it may come to the ground state with the emission of radiation, so those radiation will be called as phosphorescence. Second, it may undergo fragmentation, for which we will study here the Norris type 1 and Norris type 2 reactions. Then rearrangement reaction, where we will see the cis trans isomerism reaction, dipi arrangement reactions, oxygen addition reactions, like that. Then internal conversion, the molecule may go through the internal conversion or it may undergo sensitization, where we have seen about the p-type delayed emission of fluorescence, where one of the molecule transfer its energy to the second molecule. Initially, for this we will see some reaction which are the sensitization reaction, where that is the oxygen addition reaction is being there. We will see that. So the main reactions will be fragmentation reaction, rearrangement reaction, and sensitization reaction. So these three types of reactions we have to study in photochemical reactions. Now, cis-trans isomerism. Cis-trans isomerization can be easily worked out with the help of electromagnetic radiation. So initially I have drawn the structure of steel bean. Just you focus on the structure, that is steel bean. pH, C double bond C, pH. So here initially that steel bean molecule will absorb some amount of radiation. So here I should have written H nu. So on the absorption of those radiation, the molecule will get promoted to the singlet state. So it is the first singlet state, excited state. Then molecule will cross through the intersystem crossing and come to the triplet state. Now in triplet state, this bond will have the parallel spins. The second pi bond will be having the parallel spin, and this bond can rotate. So as a result, the spin may remain parallel, or the bond may be, if the bond is rotating in at that time, the bond may remain same as it is. As you can see, the position of the bond is remaining same as it is, and here you can see the C structure is being transferred to the trans structure first. Then as these are having the parallel spins, it has a tendency to undergo spin inversion, and as it is being staying in the triplet state, so it will undergo first spin inversion, as a result of which spin will becomes anti-parallel to one another, and as a result there will occur bond formation. So this cis reactant is converted to the trans product. So this is called as cis trans isomerism reaction. Also, the possibility may be that you will again get the cis product. So the cis product which is generated will again undergo the same reaction and will give you the trans product. So this cis trans isomerization proceeds with the diradical mechanism where these are the two radicals. And as you know, you have already studied the reaction where we say that when some amount of H nu is being there, at that time there occurs the formation of two radicals. So this is a diradical mechanism and it reacts with the triplet state. In triplet state, pi bond is broken and generate the diradical where the two electrons experiences parallel spin, and these two parallel electrons can form bond with each other by spin inversion process. But before spin inversion, carbon-carbon bond rapidly rotate and it produces both alkane, that is cis and trans, and cis again undergoes into the excitation and react with same fashion. Finally, we recover the trans alkene as a major product. So this is the cis steel structure which we have already studied, and it gives the product which is the trans steel. Now this is the practice examples where pH and double bond and pH will give you the, this is the cis reactant, it will give you the trans product. You can see the mechanism will be, firstly this will be in the S0 state. From that S0 state it will go to the S1 state. From S1 through intersystem crossing it will reach to the T1 state. In T1 state, that second double bond will form the diradical, and after the formation of diradical the bond will undergo what we say rotation. So after rotation it will form the trans structure, and then it will undergo the spin inversion where the spin will becomes anti-parallel, and there again will the bond will again get formed, and in this way you can get the cis structure will be converted to the trans structure. And this is the another example which is asked in the set exam. Just you focus out the number of carbon atoms and how you have to convert cis structure into trans product. Just the remaining entity will be fixed. Just you have to convert this cis structure into transform. Now the second reaction is photophrase rearrangement reaction. So here in case of photophrase rearrangement reactions, the phenyl acetate, this is the group phenyl acetate, upon irradiation with proper electromagnetic radiation, the reaction proceeds via radical mechanism. Here there is only the radical mechanism where it generates ortho or para hydroxyacetophenone. So here you can see this is the phenyl acetate group, that is CH3COO, and this is the phenyl ring. So this is the phenyl and this is the acetate group. So phenyl acetate on irradiation it will form the radicals first. So oxygen, this bond will get broken down and it will form the two radicals. One radical will go with CO and one radical will be there on oxygen. So they have formed this species which is the phenoxide radical as well as the acetyl radical. Now this phenoxide radical will have a tendency to form bond with this carbon. So this oxygen will have a tendency to form the bond with this carbon. So at that time this bond which will be having the two radicals, so one of the radical from this bond will form the bond with this radical, and the another radical will get open at the ortho position. So for that I have written this structure where that radical has formed the bond with the carbon, and this radical has been opened itself on the ortho position. Now it has the two possibilities that this radical can combine with the COCH3 radical and will give you the species. So this species, it is a keto species, but here you can see here double bond will not be there. So in order to get the stabilized structure, six-membered ring, this is the keto structure, we will have to convert into the enol form. And for that we write, that is when you are having CH3 C double bond O CH3, or you can see the CH2S structure or CHH structure, at that time the proton will get abstracted there, and as a result the bond will be shifted towards this position, and as a result oxygen will become negative, and that hydrogen will go to the oxygen, and as a result you will get this enol structure. It means when you are having the C double bond O structure, you can convert that structure into the enol form where the double bond will be shifted to the adjacent position. So this is the structure see double bond O. Here there is no double bond, but you can see here this is the structure which is having a double bond. So it is a 6-membered stabilized ring, and as it is having the hydrogen bonding interaction, so it will be the stable product. So it will give you, it will be obtaining more yield as compared to the another one. Now the second possibility is that this radical can combine with this radical, and this radical will get, one of the radical will get open at the para position. So you will get this type of structure. Now the radical will be at para position. So at para position, the COCH3 will get join itself and it will form this structure. Again, this is the keto structure. You will just write it into the enol form so as to get the stabilized product. But from ortho and para, ortho product will be in more yield as compared to the para product. So this is the ortho hydroxy acetophenone and this is the para hydroxy acetophenone. The similar type of reaction is given here, that is NH3COCH3. This is your practice session. You can practice it on your own. Initially, you can see here NHCOCH3. So NH bond has been this NHC bond has been broken down into the with the formation of two radicals, and these radicals will again have the tendency to form either the bond at at either at ortho position or at para position. So at ortho position, they have formed the bond like this, and because of the hydrogen bonding interaction, it will be ortho position will be more stable, and this is the para position bond. Now, next rearrangement is dipymethane rearrangement reactions. So it is the simple one, just 1,4. You have to practice it on your own. Just you have to draw the reactions, how the bonds are being moving, or how the radicals are being combining with one another, how they are dancing with one another. So here 1,4-diene, this is the 1,4-diene rearranges to vinyl cyclopropane. This is the vinyl cyclopropane group, and this reaction is called as the dipymethane rearrangement reaction. Now this is your 1,4-diene on the absorption of some amount of radiation, as there is the double bond is being there, so pi bond are being there. So because for that the transition will be pi to pi star transition. So initially they will be going to the S1 state, from that it will go to the triplet state. The square brackets are given here because these states are the not stable states, metastable states are being these, so they should be written in the square brackets. So now these bonds, one of the bond will get open and it will form the parallel spins. So there will be the formation of diradical is being there. Now as this bond will be again having the two radicals, so one of the radical will combine with this radical. As a result, one of the radical will be at this position. So as this radical is forming the bond with this radical, so I have drawn the bond within those, and one of the radical is being here. So this is that radical. Now this radical will have again tendency to form this bond with this. As a result, this bond, out of which one of the radical is being forming the bond with this, and here at this position there will be the one radical will be there. So I have just formed the bond at this position. For that I have written this. Then this bond will be like just like that. Now I just have rotated this bond into this way so as to give the stable conformation. So this is the two radicals again there. Now under spin inversion, they will form the, after undergoing spin inversion, they will form the bond and you will get the vinyl cyclopropane as a product. It means that 1,4-diene rearranges itself to vinyl cyclopropane. So these are again the examples for those. So here you can see, here they are CH3 group, and here these are the pH groups. So out of these, the substituents where you will form the diradical first. So diradical will be formed, you just remember the reaction. In this reaction you will have to rotate the bond, and for that bond rotation you should, the bond which bond will rotate, which will be lighter in weight. As you can see, phenyl will be having more weight and this CH3 groups will be having the lower weight. So you should form the bond, should form the diradicals from this side. So For that, I have formed the radical from this side, that is CH3 first, and then the reaction will be same as that we have already seen. The same type of rearrangement is again there. Here, when you will get some structure, you just focus out on your reactant and what is your function group, as we have been studying the diphylmethane rearrangement. So what may be the structure, this type of structure they should give you, but you just focus on this is the 1,4-diene structure. Here you are having the double bond and here you are having the double bond, so it is a 1,4-diene structure. So initially they will go to the triplet state, then sorry, they will go to the singlet state, then they will move to the triplet state, and then they will form the diradical at the position, and after that the diradical which is being formed will form the bond with this entity, and as a result of which the bond will get formed, and this bond will get open up at this position, and it will undergo the spin inversion, and it will give you the cyclopropyl benzyl entity as a product. Again the same reactions, just you focus on your 5 bonds, 1,4-diene structure. So it will form the diradical, then it will form the bond. As a result, the radical will get open here, then the bond will get smoothed at that position, and your benzyl structure gets converted to the pentyl structure. Just practice it. By practicing you can get it. Now here if you are having the structure like that of alpha gamma unsaturated carbonyl compound, so here C double bond C structure is there, and here this is the C double bond O structure. And in that case, as C double bond O bond is there, so N2 pi star transition is more. As a result, sorry, N2 pi star transition will be there. So initially the molecule will go to the singlet state, then it will go to the triplet state, then there will be the formation of diradical. Now at which side the diradical will be formed? So here the diradical will be formed at the oxygen site. Why? Because the C double bond O binding energy is greater than that of the C double bond C binding energy for the binding energy for the C double bond C bond. CO formation occurs rather than C double bond C. So here initially this will form the bond with this, as a result of which just the same process will be there. Just focus on that. Here the C double bond of binding energy is more than that of the binding energy of the C double bond C. As a result, the diradical will be formed at this structure. Now, photoreduction of ketones and aldehydes. Next reaction is photoreduction of ketone and aldehyde. Here you just focus on your reactant is R C double bond O R on absorption of some light energy and in the presence of protic solvent. It has the two possibilities: either it will give you the primary alcohol or it will give you the diol. Now, what will be the product? It will depend on the solvent. Now, the group which are attached with the solvent, if they are the stabilizing group, then if here the alkyl group which are being there means if your reactant is having some alkyl groups which are being having the stabilized structure, then it will give you the diol. Let's see the reaction first. Here you can see RC double bond O, this is your reactant species. It will be undergoing first singlet state, then it will undergo the triplet state. Now it will form the diradical. The diradical will have tendency to attack with the protic solvent, which is R C CHOH R dash. So R dash CHOH R dash. So one of the hydrogen as a radical will form the bond with this. So it has formed the bond with the, as a result it is carbon is having the one radical. Now as this is the CH, so that second hydrogen, that is as a radical, can combine with this carbon, and as a result it will form the RCHOHR, and this the one radical will be at this position, that will again undergo spin inversion and it will give you the ketone. Means whatever the protic solvent you are using, it will be undergoing it will form itself ketone, and what was your reactant, which is what which was earlier ketone, you are getting the solvent. So from your reactant, you are, which is a ketone, you are getting the primary alcohol. No, not primary, it is a secondary alcohol. And what, and the protic solvent was there, it is being converted into the ketone group. Now if R dash group is radical stabilizing and R is radical destabilizing, then you will get this secondary alcohol as a product. Now if R group is radical stabilizing, initially what I have written, if your the alkyl group from the reactant, if it is destabilizing, then it will give you the secondary alcohol. But if R group from the reactant is radical stabilizing, then if it can stabilize the radical, then it will give you the diol entity. Means I have just directly taken this species. I have directly taken this species, that is R C radical OH R. So these two radicals can combine with one another and form the bond after undergoing spin inversion. Now I have taken two examples for that. Initially I am having the reactant, that is pH. These are my reactant entities. pH, that is benzophenone group, where phenyl rings will be the radical stabilizing group. And as the reactant is stabilizing, so alkyl group is radical stabilizing there. So as a result, we will expect the product into a diol. Here you can see the reactant species is phenyl group, and your protic solvent is attached with the isopropyl group. Now comparing the isopropyl with the phenyl ring will be more stabilizing. So as a result, we will expect the product as a diol. Similarly, if we go on taking the reaction, that is CH3 double bond of CH3, and this is your protic solvent. Now you can just see this structure is more stabilizing than this one. It means the R group from the reactant is radical destabilizing. So as a result, it will give you the secondary alcohol. So as a result, you get the product CH3CH, CH3CHOH, CH3. Now next reaction is orthoalkylated ketone. We have already seen in this reaction, that is if photoreduction of ketones and aldehydes. If radical group is stabilizing, then it will give you the diol. And if radical group, this group is radical destabilizing, then it will give you the secondary alcohol. So orthoalkylated ketone in the presence of electromagnetic radiation, and instead of undergoing reduction, it undergoes into enolization. So initially we have seen the reaction, which is the photoreduction of ketone and aldehydes. Now this reaction is where the orthoalkylated ketones. So this is the ketone entity, and alkyl group is being present at the ortho position. So this is a orthoalkylated ketone. It, in the presence of electromagnetic radiation, it is not undergoing the reduction reaction. Instead, it is undergoing some enolization mechanism. So for that, it will undergo first singlet state, then it will undergo the triplet state, then the same entity I have written, then this bond will form the diradical. So the diradicals are being formed here. Now CH3 group, I have splitted that CH3 into CH2H group. Now that H group can combine, that H radical can combine with the oxygen radical and form the bond with that. And this is the COH bond has been formed, as a result of which one of the radical will remain at this CH2 group. So this radical. So there are, this is the diradical again. Now this is the double bond. So this double bond will again be having the two radicals. So one of the radical can combine with this radical, as a result of which there will occur this bond formation. Also this radical can combine with this radical and there will occur the bond formation. So your structure has been converted to the enol form. So this is your reactant species, which is a keto, that has been converted into the enol species. So this is your just expected product. You don't have to focus out on the other reactions. But during NET exam, they will ask you this question like that. this is your A reactant, this is your B reactant, it is reacting with C and it is giving you the product D. So if this is your, that is CO2 80, C triple bond C CO2 80 is being going to attack on this position, then this will be the 4 and I think this is the dyne. This, there is some reaction, that reaction will occur here and you will get the product like this. Now Pattern-Bench reaction. So here in Pattern-Bench reaction, it will be asked in your MSc exam also, that is the addition of double bond of alkene to give oxytocin as a product, provided triplet energy gap is for N to pi star transition for of a ketone must be less than the triplet energy gap of pi to pi star transition of a ketone alkene. That is, I have written here, that is N to pi star for ketone should be less than that of pi to pi star for alkene group. So for that N to pi star, this is the, just see the red structure where this is the N2 pi star energy gap for ketone should be less than that for the pi to pi star energy gap for the alkene. And if it is so, then only you can get the Pattern-Bench reaction. So in this reaction, the molecule which is the benzophenone, initially on the absorption radiation, it will show the N to pi star transition as there is the species is C double bond O species. So firstly it will undergoing singlet state, then it will be undergoing the triplet state. In triplet state, it has the possibility that the another reactant will have the tendency, it will react from this side or it may react from this side. Now because of the steric hindrance, this attack is quite not probable as compared to this one. As per the structure they have shown. So let's see, it has the possibility to attack in this way or to attack in this way. So this is the isobutane group. It has the two possibilities to react. Now when, as this is the double bond, that double bond will form the diradical and those two radicals will get combined with these radicals after the spin inversion. So for that I have written all this and we will get the structure like this. So this is called as the oxytane. So in your MSc exam, they will ask you about the oxytocin formation reaction. Just give a description of oxytocin formation reaction. So for that, you will have to write this Pattern-Bench reaction and its condition, which is the must condition. That is, the N to pi star energy gap for ketone is should be must be less than that of the pi to pi star energy gap for the alkene. So the second possibility is that it should react in this way and it will give you this structure. Now, when norborane reacts with the benzophenone pattern, to which reaction proceed in a direction to give its corresponding oxidant derivative. So in that case, if benzophenone is reacting with the norborane, at that time, just uh, it will react in this way and you will get this species. This is the expected product. Now, when we are saying about the benzophenone, that is PHC double bond O, when it is reacting with the norborane, at that time it is giving us the oxidant and derivative product. Now, here in this case, N to pi star energy gap is less than that for the pi to pi star energy gap for alkene. Now, if we are taking the example of acetophenone, then in that case, that is PHC double bond OCH3. In this case, the N to pi star energy gap for this transition is having more energy than that for the pi to pi star transition. So instead of giving the product as the oxidant derivative, it will undergo the dimerization reaction, and this reaction will be occurring under the p-type delayed emission of fluorescence. So in this case, the N to pi star energy gap, so here in this case, N to pi star energy gap for that ketone is more than that for the pi to pi star energy gap for alkene. So as a result of which, this group, that is C double bond O group CH3CO PH group, will sensitize the norborane group, as a result of which that will undergo the dimerization. So So here PH3 C double bond OCH3 group, initially it will undergo the transition of N to pastar, then it will reach to the singlet state, then triplet state. Now in triplet state, it will combine with the norborane group, and in that, and it will sensitize that norborane group, and as a result it will come back to the ground state. As it has been, as it is being sensitizing the norborane will undergo for singlet state, then it will undergo the triplet state, and in that triplet state it will form the diradical. It will combine with the another same norborane species, and in this way, that is dimer here in, we have already seen this, and in this way this will form the dimer as a product. So it has been observed here that when acetophenone reacts with the norborane, instead of patternobenzene, that is 2 plus 2 cycloaddition takes place via the radical mechanism, that is alkene dimerization, because the triplet state energy gap of acetophenone is more than that of the triplet state energy gap of alkene, which we have already seen. Therefore acetophenone sensitizes alkene and itself rebound back to the ground state, where after sensitization, alkene attains the triplet state and it undergoes dimerization. Now, photodimerization of alkene. Alkene undergoes into 2 plus 2 cycloaddition. As we have seen here, the case of norborane, here this group, it will, which has been sensitized by itself to that this group which has been sensitized by this reactant. So it has formed the two radicals, diradical. The one of the radical will react this with this radical. As a result, one of the radical will get open at this side. That radicals will be having the parallel spin, so they will undergo the spin inversion, and after spin inversion there will occur the formation of bond. So photodimerization reaction is nothing but the 2 plus 2 cycloaddition reaction. Now here you can see this these are the pi bonds, and they will give us this as a product. Now initially the alkene, that is ethene, will undergo pi to pastar transition. On the absorption of radiation, it will move towards singlet state, excited singlets, first singlet state S1 state, then it will move to the T1 state, and in that T1 state it will form the diradical. The diradical will have a tendency to form with the bond with the another reactant, and one of the radical of another reactant will get open on at the upper position, and as a result of which the two radicals will be there with parallel spin. Now they will undergo the spin inversion and they will give you the cyclobutane as a product. So when two ethene molecules combine, they will give you cyclobutane as a product. You just focus on the 2 plus 2 cycloaddition here. It will form with this and it will form with this. As a result, you will get this as a product. And just write down the mechanism, how the reaction will occur. Again, the same things. Just focus on 2 plus 2 cycloaddition reaction, how the bond will get formed. Just write it on your own in your notebook and practice the reaction. Now, the next reaction is photodimerization of cyclic alpha beta unsaturated ketone. Now, this cyclic alpha beta unsaturated ketone. Initially, we are having a cyclic alpha beta unsaturated ketone, which will be this species, that is C double bond O, and this is the hexanol ring, which is having a double bond with itself. So, when two of these combine, at that time, what product we will expect? So in polar solvent, there will be the head-to-head addition takes place. As a result, this bond, which will be having the two radicals, at that time the radical will form the bond with this. As a result, this radical will get open, the bond which will be having the two radicals, one of the radical forming bond with this radical, so one radical will remain there. So this radical, as these two radicals are there, so they will undergo the spin inversion and they will give you the product. So this is your product. Now, in case of non-polar media, the head to tail addition will be there. That is, you can see C double bond O is at head position, and here you can see the C double bond O group is in the tail position. So the same reaction will be there, just the product which we are expecting it's head to tail in case of non-polar media, and if it is a polar media then you will get the head to head addition. Now photooxidation, it is a sensitization reaction. So photooxidation reaction, initially oxygen which is in triplet states, that is if this is the S0 state, the S0 state will be associated with the triplet state, that is T0 state, and that T0 on the when the molecule is living in T0 state, on the absorption of radiation it will be promoted to the T1 state. And for this we have just studied the two mechanisms there. If when we say the molecule will come from T1 state to S0, then it is a allowed transition. But if we are saying the molecule will go from S0 to T1 state, then we say it is a spin, it is a not allowed transition. So for that, that can be made allowed with the presence of oxygen, as well as that can be made possible with the presence of heavy atoms. So we have already seen it in the earlier lectures. So here oxygen which is already in the S0 state, it will move to the triplet state, that is T1 state, and through intersystem crossing it will be going to the S1 state by the absorption of some amount of energy. And this we have seen I think in A-type delayed emission of fluorescence. So here what happens, let's read it. Addition of oxygen atom over an organic molecule in presence of electromagnetic radiation is called a photooxidation reactions. Means if you will be having one organic molecule and you just have to add the oxygen species in that. So generally oxygen atom is not irradiated directly by electromagnetic radiation, but its singlet state is achieved by sensitization of fluorescein or rose bengal. Oxygen atom is not irradiated directly by electromagnetic radiation. Means this is not possible directly by the irradiation of the electromagnetic radiation, but its singlet state, that is this singlet state is achieved by sensitization of fluorescein or rose bengal. Means during this intersystem crossing, when the molecule is in T1 state, it will combine with the another species and it will give its excess energy to the oxygen, as a result of which oxygen will be promoted to the S1 level, and from that S1 it can come back to the ground state or it may undergo some reaction. Now, photooxidation of diene. So we have seen oxygen is not directly undergoing S1 state. So for that, it is undergoing the sensitization with fluorescein or rose bengal. So for that, I have written the cirrus. So after sensitization, it will be going to the singlet state, and in that singlet state it is having the two radicals, and those two radicals can combine with these two pi bonds, and it will give you the cyclic peroxide as a structure. As you can see, the two radicals will be there. One of the radical will form this with the bond with this radical, as a result of which this bond will get shifted toward this position, and this bond will be formed with this oxygen, and as a result you will get this cyclic peroxide as a structure. Now I have just given the reaction where I have to add the oxygen, so you will have to practice it. So here the addition of oxygen will be, the oxygen will be added at this position, as a result the bond will shift at this position and this bond will be formed, this bond will be opened with this oxygen, and as a result you will get this as a product. Now if it is undergoing the catalytic reduction, then under catalytic reduction it will absorb the hydrogen, and as a result that oxygen will get broken, the oxygen bond will get broken down and it will form the hydroxide structure like this. So this is our product. Now if it is undergoing the oxidation reaction where MnO2 is being added, then at that time the oxidation will be there, as a result this this structure, that is hydroxide group, will be replaced by the keto group, as hydrogen will be abstracted because of the oxygen. So H2O might get removed there, and you will get this quinone as a product. So the same reaction is again, just focus on the main your functional groups. These two bonds, double bond are being there, oxygen will be added at these positions. So the two bonds will get shifted in the middles. So in the middle I have drawn the bond, and the oxygen oxygen bond is being getting formed there. Now under catalytic reduction, the oxygen oxygen bond will get broken down and the structure will be converted to the hydroxyl groups, and that hydroxyl groups in the presence of MnO2, it will give you the keto structure, and that structure is called as the anthraquinone. Now again the furan ring and pyrrole ring. So here in case of furan ring, oxygen being more electronegative, it will absorb the electron cloud towards itself, as a result of which this oxygen can sense these two double bonds. So as it can sense these two double bonds, it will show the addition reaction and it will give you this product. But in case of pyrrole, the nitrogen being less electronegative, these two pi electrons will be undergoing the delocalization mechanism, and as they are undergoing the delocalization, oxygen can't sense the presence of these two double bonds, and as a result there will be the no reaction. That is, as nitrogen atom is less electronegative than the oxygen atom, hence its lone pair delocalize more faster than oxygen atom, and there will be the lesser diene character. Now photooxidation of alkenes. Now how the oxygen is being added to the alkene group. So H nu in the presence of Ceres. As you are going to add the oxygen there, so oxygen will be sensitized in the S1 state only through the presence of fluorescein dye or rose bengal. So for that you have to write here Ceres. So here it will form the dioxetane as a product, and if it is undergoing the catalytic reduction, it will give you the diol structure. Similarly, I have written the addition reaction. Here this is the group, it is combining with oxygen and it will give you this structure. This simple reactions are there. Just oxygen is getting bonded with the double bond and forming the cyclic structure, which is a peroxide structure. Now alkene containing allylic hydrogen atom. Here in this case, that is alkene containing allylic hydrogen atom, where the singlet state reacts via six-membered cyclic transition state. Let me check everything is going fine or not. Everything is going fine or okay. Now alkene containing the allylic hydrogen atom. So we have seen the addition of oxygen towards the alkene group. Now if allylic hydrogen is being present, then the addition of oxygen will take place via six-member transition state. So where singlet state reacts via six-membered cyclic transition state and produces the hydroperoxide as a product. So Ceres in the presence of oxygen, so oxygen will move towards the singlet state, that is S1 state, and it is combining with this group. So for that, this is the allylic group and this is the allylic hydrogen. So C double bond CH2 double bond CH, and here it will be CH3. So they have written that CH3 in this form, that is one of the hydrogen will be this hydrogen. Now this bond will be formed with this, as here there will occur the bond formation. So as a result of which the proton will be get abstracted with this hydrogen and this bond will be shifting towards this position. So firstly what happens, oxygen is abstracting the proton, as a result of which the bond is being formed with at this position, the bond is shifting at this position, and as here the bond is being getting formed, so in order to maintain the valency, this bond is getting opening at the oxygen. So as a result you will get this alkene hydroperoxide or hydroperoxide as a product. So in the different reaction you just have to focus on the allylic hydrogen. So if this is the reaction, that is internal double bond is there, C, so you just focus on the allylic hydrogen. This is the C first, this group, and the hydrogen which is present to the next to that double bond, so that is this position. At this position, whatever the hydrogen will be there, it will be the allylic hydrogen as it is present after this double bond. So this allylic hydrogen will be abstracted by the oxygen first, as a result of which the bond will be shifted towards this position and this bond will be opening at this position. So as a result, here there will be, instead of hydrogen, joining there will be the joining of OH group. And here you can see, as this group, oxygen has already abstracted the proton, so it has formed the OH structure. Then this is the oxygen structure, and this is the oxygen which has been joined as OH, and the bond which has been shifted because of hydrogen is this. So your this bond which is at this position gets shifted to this position. So it may be in chair conformation in the form of six-membered cyclic transition state. So this reaction may proceed via six-membered cyclic transition state through the chair conformation during mechanism. Now, again, the allylic hydrogen will be at this position. The next example here, allylic hydrogen will be at this position. So at this position, the hydrogen will be from this position, hydrogen will be abstracted, and as a result of which you will get the bond, this bond will get shifted at this position. So I have written, initially I have this bond, so I just same bond here I have written, then this double bond will be shifted towards this position. So for that I have shifted that double bond to this position, then this double bond will be converted to a single bond, so I have converted that to the single bond, and that bond will be attached with the OH group. So this will be the product. Now, photo rearrangement of alpha azoketones. This is also called as the Wolff rearrangement reaction. So alpha azoketone, upon irradiation with electromagnetic radiation, nitrogen, that is N2, is expelled with the formation of carbon intermediate, which undergo into rearrangement to form the ketene. So I know when you will be watching this video, you will think, as there will be a lot of reactions are being going through this. So just focus on 3 to 4 reactions initially, and just watch the video till 4 reactions for the first time, then again watch the video for another second 4 reactions, and again watch the video for next 4 reactions. Practice all the reactions, and then lastly make make your own notes in which you just write down the reactant and what is your expected product. So just focus on the reaction here, how the bond are being getting shifted. So this is our reactant, that is RC double bond O, RC double bond O, CR, and at the alpha position azo group is being attached, that is N double bond and double bond N. As here the nitrogen is having the negative charge, that is 1 pair of electron on itself, so it will gets open up at this position, as a result of which this bond will be opening at the carbon position, and N2 will get removed as N2. So for that, here it has been, this double bond will be shifted to this position, not like that. Here what is happening, this R group is being shifted to this carbon. So as a result of which you can see it will be the negative group. So R group is being shifting from this position to this position, that is this carbon. As a result of which there occurs the generation of carbon. So as this R group is being moving with this carbon. So you can see here there occurs the formation of C double bond O, as it is C double bond O. Then as the nitrogen is giving the electron towards carbon, so there will be the formation of double bond here. So double bond has been formed there. So as a result, they have written double bond, and then the next step will be the R group will move towards the carbon. So for that, R group has been moved towards the carbon. So in this way, there occurs the generation of carbon. Now, after the generation of carbon, it has the three possibilities, three ways to react. Sorry, not carbene, it is the ketene. So after the generation of ketene, it has the three possibilities to react. First, ketene in the presence of alcohol, it will give the ester. Second, ketene with water gives acid, and ketene with amine gives the primary or secondary amide, that is CONHR group, but it will not give the tertiary groups, tertiary amides. So if ketene is undergoing reaction with that of the ROH group, then here you can break this ROH into alkoxide radical, that is OR negative and H positive. So OR negative can combine with the CO group because it is the electrophilic group and it will be the nucleophilic group. So as a result of which both can combine and they will form the ester. So OR is, if it is OR is going with the CO, then there occurs the formation of ester. If OH is going with that of CO, then there will be the formation of acid. And if in the presence of amide, in presence of amine, if you can write RNHH. So RNH group can get joined with the CO and you will get the primary amine or secondary amine. So primary amide or secondary amide. This is the amine group and this is the amide group. And this is the amide. Now the different reactions which will occur in the, for that, the first, let's focus on the first reaction. The same here, what I have written was same as earlier explained. So going with the first reaction, here we will have the azo group. So what we have seen in the earlier slide, this is the azo group. Azo group will get removed as a nitrogen and it will give its excess electron to this position, as a result of which there occurs the formation of bond with this carbon and the alkyl group will be moving towards this carbon. So same first, if it is a azo group is being azides is being there. So in that, now azo group is being there with this species, azo group is being attached. So here initially the nitrogen will get removed and this electron will be generated on this position. So I have written here the electrons are being, means nitrogen is being getting removed and giving their electron at this position. So this group is having the electron. Now the bond, this group will have the tendency to form the bond with this. So as a result, there will occur the bond formation at this position. So you can see the bond has been shifted in such a way that there had occurred the formation of carbene here. Now, as once the carbon has been generated, it will have the three possibilities to react. If it is combining with methanol group, so it will form the ester. Now, three practice examples are being given there. First example, second example, and third example. So just you have already studied the first this example, so you can write the another examples also. So firstly, यहाँ पे सिर्फ ध्यान देना है तुम लोगों को कि जो सी डबल बॉन्ड ओ के बाजू का जो है वो वहां पे बॉन्ड फॉर्म ने वहां इसके साथ ज्वाइन हो रहा है, जिसकी वजह से जो 6 मेंबर्ड रिंग है वो 5 मेंबर्ड में बन रही है. So let's start with the first example here. This is the cyclo hexagonal ring is there and double bond and structure is there. So the lone pair from nitrogen will form the bond with this nitrogen, as a result of which the this nitrogen will open this bond at this position. As a result, this bond will get open in such a way that nitrogen will get removed. So N2 will get removed and from these two double bonds, there will be the electron pair will be there. So as a result of which the bond which will be adjacent to CO group, that is alpha group, so at that alpha position that can form the bond with this. As a result, there will occur the double bond formation, means this bond is being shifted at there. So there occurs the generation of carbene. So C double bond O, C double bond O. I am just confusing yourself with ketene and carbene, but the name is ketene here. You just don't get confused with the ketene structure, that is C double bond O, C double bond C, R dash R. So this is the carbene structure where C double bond C, C double bond O, and as it is combining with ethanol, it will give you the ester. Means your six-membered ring has been changed to the five-membered ring. So in exam, they will ask you, they will give you the six-membered ring, and they will just form the in product you will see the five-membered ring. So which reaction is this? So this is the alpha azo rearrangement reaction is being there. So the next one is this group. So it will form the four-membered ring, and this group which will form the three-membered ring. Now practice the problems on your own so you can write it in exam. Then the rearrangement of azides. So this is the RN3 group. Initially Rx, that is alkyl halide, when it combines with the NaN3 group, at that time it will form the RN3. So RN3 will be this species which will be, which we can write it in this way, that is R and double bond N double bond N. So it will be the negative structure. So as it will have a tendency to form the bond with this nitrogen, and as a result it will give the electron pair to the nitrogen and gets left itself as N2. So N2 has been left and the remaining structure is Rn. So this is the nitrene. Now azide, upon irradiation with electromagnetic radiation, it produces the unstable intermediate as nitrene. So this is the nitrene structure. Now alpha hydrogen atom containing the alkyl azide produces nitrene as an intermediate, and delta hydrogen atom containing the alkyl azide produces nitrene as a intermediate, and delta hydrogen is abstracted via six-membered cyclic transition state. Resultant diradical combines to form the pyrrolidine or derivative of pyrrolidine. Let's see the structure. Delta hydrogen atom first. So this is the species which is having the delta hydrogen atom. Means this is alpha, beta, gamma, and delta. So at this position, with this CH3, the hydrogen which is attached, that is called as a delta hydrogen. So initially, there will be the generation of nitrine on the absorption of radiation, and as the nitrine has been generated, that nitrine will abstract the delta hydrogen from that position. I have written this in this way. So here, that delta hydrogen will be abstracted with this nitrine group, as a result of which one radical will be with this and one radical will be with nitrogen. So that can form the bond with one another, and you will get this pyrrolidine as a product. Now the another example is alkenyl azide. So this is the alkenyl azide. Upon irradiation with electromagnetic radiation, nitrogen rearranges to form the azirane. So you can see here, this is your alkenyl azide. N3 is the azide species. So N3 initially they will form the nitrine. So after the generation of nitrine, what will happen? It will undergo delta hydrogen abstraction. So before that, what is being occurring here? Let's see the reaction. So here, as it is a cyclic structure, so nitrogen has been generated. Now this nitrogen will be having the two electrons. So one of the electron will have, and this double bond will be having again two electrons. So the two radicals will be there. So one of the radical will combine with this radical. So there will occur the formation of double bond there. And the one radical is been remaining there, and this bond will again get the one radical at this position. So as a result of which they can combine. So these two radicals will combine and they will generate the structure which is called as the azirane. So here internal double bond has been converted to the outer double bond for azirane. So C double bond N, and this is the CN group. So this structure is called as the azirane structure. Now, if it is a cyclic structure, the reaction will proceed with this mechanism, which is simple fine structure. And if the open structure is there, then there will be the abstraction of alpha hydrogen. So here you will get cycloalkane as a product. Now, if alpha carbon atom bear the substituent, then now if alpha carbon atom is being bearing some substituent, at that time that alkyl azide undergoes into 1,2 shift and produces imine as a shift base. So you can see that alpha carbon is being having substituent. It is not free. It is being substituted with the alkyl groups. So initially there will occur the generation of nitrine. So nitrogen generation is being there. Now what happens? One of the radical will form the will gets will this radical will form the bond with this carbon at that time, as a result of which the bond from these two radicals, as I have shown the arrow upward, so I will show you from this position, as this bond will be having the two radicals. So one of the radical from this bond will combine with this radical, and as a result of which it will get removed itself as CH3. So that CH3, which is again the radical, will combine with the NH3 and radical, and as a result of which you will get this species, and this is called as imine species, and this is called as 1,2 shift. Means here from first position, that CH3 group has moved towards the second position. So it is called as the 1,2 shift. And it is the imine, and it is this reactant is being used as a shift base. Now, Norris type 1, in your just 5 minutes more for this. In photochemistry, you will have to focus out on Norris type 1 and Norris type 2 reaction. These are the main reactions which are mostly asked in exam. So Norris type 1 reaction, the aldehydes and ketone in presence of electromagnetic radiation by N to Pascal transition undergoes into alpha cleavage, and these are called as the Norris type 1 reaction. So just focus on this reactant. This is my reactant species, that is cyclohexanon group. Now this cyclohexanon, on the absorption of radiation, it will show into Pascal transition, and that transition it will go to the singlet state, and then it go to the triplet state. Now when it is moving towards the triplet state, it has the three possibilities: first, second, and third. Now in the first way, the aldehyde and ketone, they will undergo the alpha cleavage. Alpha cleavage means this bond means this, either this will be alpha position, or you can say this will be the alpha position. So this bond will undergo breaking. So as a result, the alpha bond here, instead of alpha bond, I have formed the two radicals. The bond has broken in such a way that it has formed the two radicals. So there are the two radicals I have written. Now this radical will absorb the hydrogen from this position as a radical. So as a result, it has formed itself as a unsaturated aldehyde. And as the radical hydrogen will be living as a radical, so one radical will remain at this position, which will combine with this radical, and it will form the unsaturation character. So this is called as the unsaturated, as it is unsaturated species, and this is the aldehyde. So this is the first step. Now second step, and this is the most important step on which the reaction will be there in exam. Second step, just focus on the second step mostly. So in this case, that alpha cleavage will be there, so there will be the formation of two radicals in triplet state, and as a result of which the CO will get removed as CO, and here as CO is being getting removed, there will be one radical at this position. So that radical will undergo spin inversion, and they will form the bond with themselves, and as a result, from this position CO has been removed, and they form the cyclopentane group. Means cyclohexanone has been converted into cycloalkane, cyclopentane. So this is the decarboxylation reaction. Now the next reaction will be the alpha cleavage will be there, and for that alpha cleavage, I have just, instead of writing in this way, I have just, instead of writing the bond in this way, I have just written the bond in this way here. So here you can see this bond. So the alpha cleavage will be there. So after the alpha cleavage, that hydrogen abstraction will be there. What will happen? The hydrogen will be abstracted through this radical. As a result, it will get stabilized as this position. Okay? It means there has been formed the formation of CH3 group. Now, the as radical is being there, one radical is already there. So the radical formed from hydrogen will combine with the radical from CO, and there will occur the formation of double bond with themselves. So there occurs the formation of ketene structure. So this is called as the ketene, and we have already seen the reactions of ketene in the earlier reactions. which are the photo rearrangement of alpha azoketone, where after generation of ketene may undergo these reactions where it may undergo the ester formation in the presence of ROH, it may undergo acid formation in the presence of acid, in the presence of water, and it may undergo the amide formation, primary or secondary amide in the presence of amine. So this is the ketone structure. So in Norris type 1, alpha cleavage will be there. So first possibility of alpha cleavage is unsaturated aldehyde. Second possibility of alpha cleavage is cycloalkane formation, and third possibility is ketone generation. Now the example for that. So just focus on this example. Focus on this example first. So you are having this structure in the on the absorption of radiation, either it will give this species or this species. So as you can see here, the CO group is being removed from the product. It means it will be the Norris type 1 reaction where CO gets removed. So in how will you write the mechanism for Norris type 1? So alpha cleavage will be first there. So for that you will break that bond and you will write the two radicals, one with CO group and one with this carbon. So as a result, I have written, see here one radical is there and here the another radical is there. Now CO will get removed. As a result, the two radicals are like this. Now this radical and this bond will be like this. Now these two radical will undergo spin inversion first and they will form the bond. The two possibilities will exist there. Either this mechanism will be there or this mechanism will be there. So first possibility is that the formation of cyclic ring structures, or the second possibility is that one of the radical will combine radical with the radical from this bond, and as a result there will occur the formation of double bond. And as the one radical will remain pending here, so that radical will combine with this radical and you will get this structure. Now the same reaction was that. Now the another example for Norris type 1 is this. This is the reactant and this is the product. So this you can see this is just a rearrangement reaction where your internal double bond has been converted to the external double bond. So here in case of Norris type 1, you can see we have already seen about the rearrangement reaction. We have already seen the unsaturation character, unsaturated aldehydes formation. So let's see what happens here. Firstly, that this molecule will undergo the alpha cleavage. So alpha cleavage will be there. As a result, there will be the generation of two radicals. One radical will be with the CO and this radical with this carbon. So I have written the two radicals. First radical and second radical is there. Now they have formed the 5-membered ring. So 1, 2, 3, 4, 5. So as the fifth carbon is having the double bond, so one radical can combine with the radical from the double bond. So for that I have written like this. So this radical can combine with this radical. As a result, as this radical out of the double bond, out of the double bond, one radical will combine with this double bond. As a result of which one radical will remain pending there. So that radical can form the bond with this radical. So initially I have formed the double bond, that is this bond has been shifted to this position. So the bond which was at the fifth position has shifted itself towards the sixth position first. Now fifth position is having the radical, so that can combine with the CO, and as a result of which you are getting the beta gamma unsaturated ketone. Now what is quantum yield? The quantum yield is the ratio of total number of molecules reacted to that of the number of Einsteins absorbed. So quantum yield is equal to number of molecules reacted to that of n times h nu. So as we know that, just we have seen when the molecule is absorbing some amount of radiation, it is promoted to the higher excited state. So in that higher excited state, it has different possibilities. It may undergo internal conversion, it may undergo intersystem crossing, it may undergo quenching. So during that, very less possibility is that it will undergo the reaction. So as a result, if we are saying that 10 molecules are being absorbing some amount of radiation, then out of which 2 molecules are being reacting there. So as a result of which 2 divided by 10 multiplied by 100. So quantum efficiency will always be less than 100 in that case. Now This is the Norris type 2 reaction. We have seen about the Norris type 1, which is the alpha cleavage reaction, as a result of which we are being getting the unsaturated aldehyde, we are getting the cycloalkane, we are getting the ketene. And we have seen this example for Norris type 1. Now, Norris type 2 reaction. In this Norris type 2 reaction, the gamma hydrogen atom containing aldehyde and ketone, ester, acid, etc. They shows type 2 reaction where delta hydrogen atom is abstracted to a cyclic transition state. So, as they are showing the gamma hydrogen atom, just focus on the gamma hydrogen in case of type Norris type 2 reaction. So, this is your reaction which is having the alpha, beta, and gamma position. So, gamma hydrogen will be abstracted there. Now, the abstraction will be occur by a six-membered cyclic transition state. So here, initially the molecule as C double bond O group is there, so N2 pi star transition will be there, so it will be undergo S1 state first, then it will move towards the T1 state. Now that double bond will form the di radical first. Now, as I have written the same structure in this way. Here you can see this is my oxygen atom. This is my oxygen atom. With this, I should have formed C double bond O group. Now, after that C double bond O group, this is first C double bond O, then this, just I have written the in this way. So you can see here, this is my alpha, beta, and gamma. So alpha, beta, and gamma. So gamma position is having the hydrogen with itself. So this hydrogen will be abstracted with the oxygen. So because of which it will be abstracted as a radical. So one radical will remain at this position. So as you can see, one radical is remaining at this position. So they have formed OH, and one of the radical from CO bond is being at this position already. So it has the possibility that alpha beta, after the means Norris type 2 reaction is first abstraction of gamma hydrogen and then alpha beta bond cleavage. So this alpha beta bond undergo cleavage, as a result of which this radical will combine with the bond will be broken down in such a way that one radical will be at this position and one radical will be at this position. So there will occur the bond formation. So here you will get this structure, and here as there will occur the bond formation at this position, so you will get this structure. Again, I should have written this bond also there. So this is the keto form. This is your ketone species. Sorry, the product which we have obtained, it is a enol species. That enol can be converted to keto group in this way. So I have converted that to the keto group. So this is not hydrogen, this is the keto, because they are having this. I have forgotten to write this bond. CH3 group is being there. So for that CH3, and this is the CH3. This is not hydrogen. Okay, the another possibility for this Norris type 2 is that the two radicals which have been formed, they will undergo the spin inversion, and as a result of which there will occur the bond formation with this species, and you will get this as a product. If this group is being stabilizing, then you will get the cyclobutane as a product. So in Norris type 2, what you have to just focus, firstly you have to abstract the gamma hydrogen via this state, six-member cyclic transition state. So after abstraction of hydrogen, the alpha beta bond cleavage will be there, and if the bond is being stabilizing, if this bond which is being there, CH3 group is being there, if it is radical stabilizing, then it will give you the cyclic structure. So you will get the cyclic structure like this. So this is Norris type 2 reaction. In exam, Norris type 1, Norris type 2, Paterno-Bench reaction, these are the most important examples. So again, you just focus on, this is your C double bond O group, then this is alpha, beta, and gamma position will be there. So gamma position will be, from the gamma position, there will be the abstraction of hydrogen will be there. So after abstraction of hydrogen, as this group is being radical stabilizing, you can see if this group is being radical stabilizing, so it will form the bond with this. As a result, you will get the cyclobutane as a product. Then different reactions are given there. Then this is the reaction which has been given. It is giving this product, and as it is being a fragmentation reaction that I have already told you, fragmentation reaction we have to study the Norris type 1 and Norris type 2 reactions. So in fragmentation, here you can see they have formed this bond. This is alpha, beta and gamma position. So alpha beta will undergo cleavage and they will form the bond after abstraction of gamma hydrogen, as a result of which you will get this product. So you can see just see the reactant, see the product and predict mechanism. You can predict the mechanism on your own now. Firstly, it will undergo the gamma hydrogen abstraction, and after the abstraction of gamma hydrogen, there will be the alpha beta bond cleavage, and as a result of which you will get the enol species as well as the alkene, and that enol species will undergo the ketoenol tautomerism, where you will form the keto species. In case of ketoenol tautomerism, we will write these arrows, equilibrium arrows. The second example, alpha, beta, gamma. Abstract the hydrogen from gamma position and show the alpha beta bond cleavage, as a result of which you will get the product as this cyclopropane group and this ketone group. I have written that. So these are the different examples which you can study, which you can practice. So this is all about lecture. Thank you. So basically, which reaction we have studied in this? Let's revise all those. So our focus was mainly on fragmentation reaction, which is Norris type 1, Norris type 2, rearrangement reaction. There are different rearrangement reactions which we have already seen, such as cis trans rearrangement reaction, then dipymethane rearrangement reaction, then 2+2 cyclo addition reaction. So all those are the rearrangement reaction. Then we have seen the sensitization reactions also there, where the addition of oxygen takes place through the sensitization mechanism. So first was cis-trans isomerism. Just remember the reaction. The cis reactant is converted to the trans product. So cis reactant is converted to the trans product. So this is first one is cis-trans isomerism. Second, photophase rearrangement, that is phenyl acetate is giving you orthohydroxy acetophenone or parahydroxy acetophenone, but out of which orthohydroxy will be in more product because of hydrogen bonding interaction. Then this was example. Then third one was dipymethane rearrangement reaction, where you have got this is your reactant and you are getting the vinyl cyclopropane as a product. So what you have to do, you just write down the name of reaction, its reactant and its product. So this is the third reaction, where you are getting the vinyl cyclopropane as a product through the presence of this 1,4-diene structure. Then we have seen the photoreduction of ketones and aldehydes, where if alkyl group is radical stabilizing of the reactant, then it will give you the diol structure, and if it is radical destabilizing, so here, and if it is radical destabilizing, then it will give you the primary alcohol. For that, we have taken the example where phenyl group is radical stabilizing as compared to isopropyl group. So they are giving you the diol structure, and while this group, that is protic solvent, is being its alkyl groups are more stabilizing than this, it means the alkyl group from the reactant is radical destabilizing. As a result, it is giving you the alcohol, secondary alcohol. Then we have seen the rearrangement reactions. This is the photo reduction of fourth reaction was photo reduction of ketones and aldehydes. So if at the alpha at the ortho position alkyl group is present in case of ketone, then instead of reduction, it will undergo some enolization mechanism, and for that we have seen this reaction where this is the product, enolization product. So in exam they will ask you A species is, this is your A product, it is giving you the, this is your A reactant, it is it will give you the B product, B will combine with C and form D. Then Pattern-Bench reaction we have seen here. For this Pattern-Bench, you just remember the N2 pi star gap should be less than that of the pi 2 pi star. Then only you will get the oxygen as a product. And if N2 pi star energy gap is more than that of pi 2 pi star, then it will form the dimerization product. So here they have shown if it is a benzophenone, it will give you the oxytone as a product, and if it is a acetophenone, then in that case it will sensitize to the norborane, as a result of which norborane will undergo 2 plus 2 cycloaddition and it will form the dimerized product. So 2 plus 2 cycloaddition reaction, fifth reactions. These are simple one. Photodimerization of alkene. You can say 2 plus 2 cycloadditions. Then sixth reaction was photodimerization of cyclic alpha beta unsaturated ketone, where if polar solvent is there, then you will get the head to head product, and if non-polar solvent is there, then you will get the head to tail as a product. Then photooxidation reaction. In this, you have to remember that oxygen will move to the singlet state only through the sensitization mechanism, because oxygen, which is initially in the triplet state, will be absorb the radiation, will absorb the energy from fluorescein or rose bengal, and it will promote itself from T1 state to the S1 state. So the next seventh reaction was photooxidation of diene, where you added the oxygen to the diene. So different ways you can, just you have to focus on the diene structure. On that diene skeleton, oxygen will get itself added, and it may undergo catalytic reduction, and from that, after the catalytic reduction, it may undergo oxidation, and where there occurs the generation of phenone. So in this way you can also get the anthraquinone. You just don't have to focus on the structure, you just focus on your functional group, which is a diene. So here we have seen pyrrole can't give the reaction because the lone pair is being undergoing delocalization. So oxygen can't sense the presence of diene structure. So as a result, it will give no reaction. But here, because of the more electron, because of the more electronegativity of oxygen, the bond pair will be shifted. The lone pair will be shifted towards oxygen. As a result, oxygen can sense the diene skeleton. As a result of which, it will give the reaction. So that one was seventh reaction. This is the eighth reaction, photooxidation of alkene. Ninth reaction, 10th reaction, rearrangement of alpha ketone. 11th reaction, rearrangement of azides. 12th, Norris type 1. And 13th, Norris type 2. So these are all the reactions which you have to practice and which you have to make the notes. For which you have to make the notes. So this is all about today's lecture. Thank you. Now let's again have a Google Meet and just join again at the same Google Meet, and we will see the attendance again. Thank you. The same Google Meet will be there. Join with the same link. Thank you. While watching this video, you just break the video into few parts and then watch it. Just don't watch the complete video at once. You just break it in at an interval of 25 minutes. Thank you.